Thanks for joining this week. In the ongoing IGS Global Seminar Series. This is another one of our sea ice focused weeks, and this times out nicely with the Antarctic sea ice minimum. So this week we have Dr. Vishnu Nandan, who is a postdoc across all of Canada. He's kind of everywhere, although he's presenting to us today from India. So thanks, Vishnu, for getting up in the middle of the night to give this talk. Vishnu he overwintered in Antarctica last year, and he is here to share his experience and sort of how it all went studying sea ice in Antarctica throughout the winter. So Vishnu is going to give about a 30 to 40-minute talk, and we'll have some questions after that. And then following that, Dr. Petra Heil from Tasmania is going to give a short presentation just to sort of an update on what the current sea ice situation is around Antarctica as we come to this annual sea ice minimum. So I am just quickly going to stream this to the IGS Facebook page. So just hold on a sec. Select group. And then while that is loading, I will pass it over to Vishnu.
Hi, Dave. So thanks everyone for joining in. So it's like Dave said, it's very late night in India. It's 2:30 in the morning. So I'll be talking about my overwintering efforts with Robbie Mallet. Robbie is not here. He is somewhere in UK right now. So Robbie and I, we did this wintering in the Bellingshausen Sea at the Rothera Research Station. And it was a lovely, sarcastically, it was a very lovely year for us to do sea ice fieldwork. So this title slide actually shows how difficult it was for us to do the measurements. So this is the light station, the radiometer station, with Petra's IMV also. So the station broke up on sea ice. We were able to retrieve it, but this was our whole life for like 8-9 months in the Antarctic. Okay. So the project we were involved was called as the Defiant, the Drivers and FX. Hang on. Why am I not able to?
You've skipped ahead a few slides.
Yes, because
there you go.
What I want, because this I want to hide all this.
We only see your slide. We don't see anything around it. We just see your slide.
Yes. Yeah. Okay. There you go. Okay. So the project we were involved was called as Defined. It's a British Antarctic survey project with the UK and NARC. It's called as Drivers and Effects of Fluctuations in Sea Ice in the Antarctic. So the whole idea was to actually study the causes and consequences of like sea ice decline in the Antarctic since 2016. And as part of our work package, we did the first all-winter radar observations of Antarctic sea ice in both the Weddell and the Bellingshausen Sea in 2022 and 2023. In 2022, Robbie was on Polarstern in the Weddell Sea, making measurements out on like different ice floes. And in 2023, Robbie and I, we were doing wintering in Rothera. So the objective was to actually build on mosaic observations in the Arctic and then develop satellite-based Antarctic snow depth product on sea ice using KUKA radar. So KUKA radar is a surface-based polarimetric radar that operates in Ku and Ka band frequencies. It mimics radar satellites, including Cryosat-2 Altica. Cryosat-2 is Ku band, Altica is Ka band, and the forthcoming Crystal mission, which is a dual frequency Ka and Ku band mission by ESA. And the main question we were like focusing on Antarctic sea ice was like how much snow and its physical properties, especially its complex in the Antarctic, it impacts the penetration of Ka and Ku band radar signals. It's much more less complicated in the Arctic, but in the Antarctic, with a lot of like snow dump, snow loading in the Antarctic, we get like a lot of like complex geophysical properties. So we wanted to understand like how the snow properties affect the penetration. And like I said, it's the first all-winter radar observations on the Antarctic sea ice using this radar. And the objective was to develop like a good satellite-based snow depth product. This instrument has been used before on mosaic in the Arctic, and Rosemary Willett in her paper in 2023, we were able to actually get snow depth on sea ice in the Arctic, comparing the K and KU band measurements and correlating that with magneprobe measurements, and getting like a very strong correlation between that. So we were able to actually use this radar from a fully polarimetric standpoint to get the snow depth. So we used those knowledge, what we got from Arctic sea ice, to take that to the Antarctic. So that was the whole idea. This was the team, just me. During winters, we had like a team of 25 people in Rotterdam, but Robbie is on the right, I'm on the left. So we were using this radar that sitting in the middle, using that radar to actually like measure, do like a lot of transects, a lot of like point-based measurements in Rotterdam, but the reality was different. I'll come to that in a moment. So before this campaign, before the Rotterdam campaign in April 2022, Robbie was out on Weddell Sea ice, where he actually used the radar from Polarstern on different ice flows. And what we could find was, we could find like a lot of like ice layers within the snowpack, and within the old snow also. So you had like new snow, then ice layers, and then old snow, and then sea ice. So what happened was, these ice layers that formed between the snow layers formed like melt-free cycles, and that completely blocked the radar penetration both in K and KU band frequencies to the snow ice interface. So we got like a lot of like reflections within the snow layers, which actually caused like masking of penetration of both the frequencies within the snow volume. So, but this is just like one plot, what I'm showing here. But we had like 18 different snow pits, so the spatial variability was different. So some snow pits were able to actually get the snow depth. Most of them didn't, because of the presence of like multiple like ice and snow layers within the snow volume. So that was a complication what we had in Weddell Sea. But again, we used that knowledge, and took it forward for the wintering campaign for the whole winters. In March 2023, we were off Rothera. Rothera is on the western edge of the Antarctic Peninsula, on the western side of the Bellingshausen Sea. So the best thing, with this location is that we get like sea ice in the ocean, in the Bellingshausen Sea, and we were also able to like access to the land ice glaciers, which meant that we were actually able to get the measurements both on sea ice and also on land ice, which was also a part of the defined project. As when we reached, there was no sea ice as expected. It was like completely open waters, but the landscape is absolutely beautiful. We had this, this cliffhanger in the form of like glaciers right next to the ocean, and we were able to access sea ice when it formed, right from the hangar also. So that was actually good. Supposed to be good. The first objective was to like unpack the radar. Again, it was when we get the radar from the box, it's actually easy to unpack. But when we wanted to actually get the sled from the box, we were actually not able to get it out because nail issues. We had to like do some jumping and dancing on top of the box to get the sled out of it. So that was also like challenging. The challenges started like from the very first beginning. One objective of our study was to actually do like radiometer measurements on sea ice to get the light transmission through sea ice. So we assembled, so we had to do like radiometer upward and downward looking radiometers, and also the under ice radiometers. So we had to assemble them inside the station for testing it out on the glacier first, and then on sea ice. But as when we reached our station, we were welcomed with rain in the Antarctic almost during the beginning of winters. We had like severe rain for like few days, and that was like very strange. I mean, we have seen like rain on snow in the Arctic, but rain on snow in the Antarctic was like a bit strange for us. But still scientifically it was like good for us to like experiment new things. So that was like the first few days for us. And then, we had instrument issues as expected in fieldwork. We have a saying that, if you 50% of your fieldwork works, it's a success. It was like that. So we had instrument issues with like SMP, with the light station, circuit boards, etc., etc. Thankfully we had spare parts, but unthankfully the spare parts also didn't work. So that was pretty bad for us. We had to test the radiometers on the glaciers, just to see if it works. And we had these funny moments on the glacier where we were trying to put the installation on the ice on the glacier, but yeah, Antarctica is like so super windy, so of course the winds hampered us in doing it. But we were able to deploy the light station on the ice just to get some initial basic measurements. So we had the downward looking radiometer, the upward looking radiometer, and we had a camera that was actually looking into the snow patch here, trying to see the snow evolution across time also. So we had the continuous radiometer measurements also. We didn't deploy it for a long time. We just wanted to check it first to see if it works. So that was our whole idea, and we were happy about it. I mean, that was our first success after like falling down. In between, Sir David Attenborough, the BASH ship, the research icebreaker, came in to resupply the station, and also the summer team left. And once the summer team left, we were a group of like 25 people on station for like the next 9 months. So that was like an emotional moment for us to leave, to see off these people and be alone in the station for the next set of like almost like close to a year. And once the SDA left, once the ship left, and within like few days, towards like early June, we had sea ice in the station, like starting with like very thin ice, and then growing into like small pancake ice, and also like very thin nylas. It was still difficult. It was impossible with the BAS regulations to be out on the ice because the ice was like super thin, close to like 5 to 10 centimeters. So we were not allowed to be on the ice, but at least we were able to see the ice evolution right in front of us. The problem with the ice in Rodera is that it's so windy offshore. So sorry, not offshore. Yeah, the wind from the wind from the shore into the ocean. So whatever the ice formed, it always used to blow off completely. So it was very difficult for the ice to actually form like landfast sea ice initially. So we had to wait for a long time for that to happen. And then the thin ice formed into like nylas, and we were actually able to use radar on the ice using a crane. So I'll show you a video as to like how we did that. So the idea of this experiment was to actually look at this height experiment was to look at how the height differences between the radar and the ice surface actually caused the change in the range, the radar range, and also if there is a peak widening or broadening of the range with respect to height. So we were not able to again be actually on the ice because the ice was like really thin, but we were able to use the crane to actually drop in the radar onto the ice to get like the initial basic results. So this is an example of like, as the radar went down from like 8 meters onto like 2 meters, you could actually see like a drop in the range across time. So that was like the first objective for us to actually, look at how the radar range changed across site. Especially this is a surface-based radar, so we wanted to make sure that the algorithms what we develop from surface-based radars can be like scaled to like airborne and like satellite-based algorithms. So we want to test all that initially. We were also able to do this experiment where the ice drifted across, and we were able to actually like tow the radar, like drop the radar, and looking at as the ice moved, the radar was actually able to take the scans of like different ice types. So that was also like interesting for us to look at. We haven't looked at the results yet, but hopefully we'll be able to ascertain some results based on like how the different thin ice types can be like retrieved. The signatures can be retrieved from both Ka and Ku. So this is a snapshot of like how the radar looked at. So this was looking at like a small, like a pancake ice piece. Like it's not completely pancake ice, but still, close to that, almost like in a gray whitish. And we were also able to get like the open water signatures also. After like some time, we could also see like seals popping up, poking their heads up somewhere here. I mean, I don't have a photo of that, but that was also like interesting for us to see like the seal signatures using Puka. This is another example of like how we got this thing done. So the radar was actually like almost like floating on like thin air at a particular height, while the ice was like drifting across us. So that was also like good experience for us. We were still not able to, so till the mid of winters, we were still not able to be on the ice, like, put our feet on the ice, because the ice was like really thin, and sometimes it always used to break up, just like, how I showed the drifting of sea ice there. Midwinters came in, and, we had fun in the station. So, we made winter gifts for each other. So that was also like, very nice for us to like, bond together between the stations. So this was the midwinter dinner, like a team of 25, we are all together and all. So that was fun. In between all this, we got like surprise gifts from home. So I got, like a book to read from my parents. So that was good for us. That was good for me. I'm not a reader, so I didn't actually read that book. It's still there. So, but people across the station, they got like gifts from their families during that time. It was sometime during like early July, and we didn't know that they had sent gifts for us. So that was also like emotional for us. And during midwinters, we had like this famous midwinter photo, not just in the base station, but across the whole stations across the Antarctic. So people take like midwinter photo, and they share across. So that was also like very interesting for us. And during that midwinter week, we had like a lot of fun. We didn't do any science during that week. We had like a crazy time. I don't want to explain what we did, but still. And then once the sea ice came in, then we had the field guides. They tested the ice with the box chisels. So we were not allowed to be on the ice on barefoot. We had to use skis. That was the regulation, but at least we were able to access the ice initially after the field guides. They tested the ice thickness. So initial ice thickness, the safe ice thickness was uh, the safe ice was like close to like 20 to 25 centimeters. So we were able to take the radar onto the ice, but also not in person. Before that, we wanted to install the radiometer system and also Petra's IMB from the Australian Antarctic Division. So we had the under ice camera, through this pole under the ice. Then we had like two radiometers, one looking into the ice and one looking into the atmosphere. And then we had the IMB thermistor, going into the ice. The system was powered by like batteries, and so the whole system was close to like almost close to like 150 kilos, almost close to that. So we were happy, but Antarctica is windy, which meant that we were struggling with the instrument on the ice. The ice was almost like breaking up, and like we didn't expect, and maybe we did expect, the ice broke up. That was our first disaster in the making. And the long story short, we had like instruments almost like sinking through the ice, because the ice temperature was, I mean, the air temperature went up to like +4 degrees for like almost like a week during almost like midwinters. So it was like a really bad. The winds were like super strong. Yeah, so it was really bad for us. And since we are not able to get out because of those winds, we were not able to retrieve the instruments. I was like looking like this always from inside the station, looking at the fate of the instrument. So that was me back then. And then one fine morning, the ice broke up completely. So that was a that was disaster in the making for us. Back then, we had to wait for almost like a week to retrieve the instruments, and this is how the instruments looked like right in the middle of all the broken ice piece. So we used to live here. We used to live here. So we were not able to access the land. We were able to access the land, but we were not able to access the ice because the ice had like completely broken up. We were also not able to use the zodiac to access through the ice because we were worried that zodiac would also get stuck within the ice if there was like another wind event. So this was like a drone shot with the ice completely breaking up. And if you see, we had these, yellow pelican cases with the batteries also like, completely into the ocean. So that was also like really bad. But, the field guides, they didn't give up. They tried different diverse methods to actually retrieve the instruments. So for example, the bow and arrow method. Yeah, that didn't work because it didn't go far. And one of our field guides also used the rope method to actually like sling onto that. That also didn't work because the instrument was here and the rope was able to get only on here though. That was still another like 50 to 60 meters. But still, we can't complain field guides. They are like really good. They tried for us, but didn't work. But after like a week, we were able to get across the broken ice floes, and then we were able to access the instruments, but it was in a very bad shape. So we had to use a zodiac using the boating team, and we had to retrieve all those instruments. If you can look at if you can see that the boxes, the wooden boxes with the batteries are also like sunk into the ocean. So that was heart-stopping moment for us, but we were able to retrieve it. So this was Petra's IMB. It came back in a very bad shape. Sorry, Petra, you're still there. And we were not able to get any measurements from that. The IMB measured for close to like a week, but once it was retrieved, it was like completely destroyed. So that was really bad for us. Yeah, so this was our like first major disaster. I mean, this was the only disaster we had, but still we couldn't access sea ice much after that. And when you take instruments out of the water, you would expect the instruments to be like waterproof. But this camera, if you look at what Robbie is doing, there was like water infiltration inside the camera. So the images what we got from the camera was also like hampered with leak. So that didn't also help. So on sea ice was a disaster then that time. And that was the time when we got to know that the Antarctic sea ice extent was at the lowest at that time compared to like 1986 by almost like a million kilometers. So that was like we were unfortunately fortunate uh, to be in Rodera where we had like the lowest sea ice extent. But we won't give up. So we didn't have sea ice, but we had a glacier right next by. So we accessed the glacier with the radar. So we had the station here. This is the ocean, and this was like a marine retreating glacier. But it was like it was not so steep. We were able to access it using the glacier, and we dug like big heavy snow pits, like deep snow pits close to like 2.5 3 meters to take the measurements and or measurements using puka and also like dielectrics, densities, etc., to understand like how far the radar signals penetrated through the snowpack into the fern layer. So that was interesting for us because that was also part of the project, and we wanted to know like how this works. So we dug like 3 to 4 snow pits. Every snow pit took like almost like 3 to 4 hours for us to dig through like 2.5 3 meters, but it was like worth. This is an example of like what the radar range looks like. So 1.5 is where the snow surface starts. So the range from the antenna horns to the surface is close to like 1.5 meters. So this is the snow surface. then we had like ice layers in between, which showed like, like the strong scattering from, so this is HH, horizontally polarized from both Ka and Ku. And we were able to actually see the fern layer right in the bottom. Interestingly, people may ask, like, why Ka, which has a higher frequency than Ku, has a stronger scattering and it has like a stronger penetration. We don't know that yet. So that's still bizarre for us, but we are able to actually see the Ka like penetrating deeper into the snowpack, into the fern layer. So that was like very interesting for, it's still interesting for us. We are still analyzing the data. So in the lab, so we are also doing like lab-based experiments. So one of the experiments, what we did was to actually look at how snow wicks brine, like salt, like like brine through sea ice. So on first year ice, this happens, and that has been my whole PhD and postdoc over the past many years. So we wanted to look at, like Robbie and I, we wanted to look at like what's the process that actually causes the snow to wick brine. So what we did was, we used like 20 like plastic cylindrical tubes. We shoved them, we put them through the snow at different densities, and then using a plastic boat and with like 50 ml of like 100 ppt brine, we put this whole snow inside the cylindrical tube through the plastic boat, just to give you an example of how it looked like. And when you insert the snow core into the dye, you would actually see the brine wicking up, and you would actually see like the lot of concentrated brine in the bottom with the diluted brine towards the top. So yeah, so so you wanted to look at like how much brine actually wicked up from the bottom of the snow into the snowpack, like the brine wicked height. We also wanted to see like how much brine rejected back into the boat as a function of like how dense the snow is. So we did two experiments in August and in October between soft snow and hard snow from just outside the station, from land snow only, because we were not able to, we wanted to make sure that the snow was fresh so that we could introduce brine. And then when we took the cross section of, this, once the brine wet, this is how the cross section looked like in terms of like how the brine wet from the base into the top. So this was what we wanted to look at. Just to give like a very brief results of what I mean, we have submitted this paper to the Annals of Glaciology for now. It's in review now, but long story short, as a function of as a function of like how much the basal bulk salinity was, as the basal bulk salinity reduced, the brine wicking height increased. So that's the whole point. So as the brine rejection also increased, the brine wicking height also decreased. So the more wicking we had into the snow volume, through the snow volume into the top, the basal snow salinity also decreased, and the brine rejected volume also decreased. So that was like the takeaway for us. There is no clear relationship between like how hard and how soft the snow is with respect to the brine wicking height, the height. That is still under like experiments. We are still trying to like figure that out. But we were actually able to see the brine wicking, from the base into the top. So that was like very interesting for us to actually look at the process. And once we were doing all these experiments back, the ice which broke up earlier, it came back again. It was beautiful. We had this, nacreous clouds, which actually looks, it looks like a rainbow in the sky. That was beautiful. We had we had like a big widespread, like not smooth, like heterogeneously smooth proliferation of like frost flowers. When the ice came back, we were still able to access the ice with skis, but not with the radar. But we won't give up again. So we used a pulley system. We used a pulley system on the ice to actually use to tow the radar on thin ice. So as the ice moved across the ice, it was actually able to get the measurements across the transect. And once we finished the transect measurements, we pulled the radar back into the land, and then we went out uh, to take the geophysical measurements. That's what we did always initially. Uh, this was, what happened when we had like thin ice. The ice was completely flooded. We had like thick dump of like snow close to like 30-35 centimeters almost. And we had like, but the best thing was, we were able to measure this flooding and also the slush using the radar. We don't have the results yet. It's still under quality control, but we were actually able to measure like the negative freeboards and the formation of slush and also the snow ice within the snow volume. And this was how the snowpack looked like. So this was, I mean, across the flow, we had like multiple heterogeneity in slush. We had like regions where we had like flooding close to like 10 centimeters. This was like close to like 1.5 to 2 centimeters. And what you could see is you have this strong flooding here, and you could see the wicking of like the salinity, the brine through the snowpack into the top layers. And this was what we wanted to see. We saw from the lab experiments using the dye also, but on real CA we saw this like clearly. This was one of the most interesting pits, the snow pits, what we had, where we had like almost like a strong layering of like snow, and below that you had like this hard, briny, like salty crust of snow, which we think that when the ice flooded, it created this brine layer, and then when the freeboard went down again, it froze up into like snow ice. So this is almost like snow ice layers, and then you had this like this strong this brine wicking throughout the snowpack into the snow volume. So the question for us right now is, where is the scattering coming from? So is the Ka scattering coming from the air snow interface? Ku is actually coming from the dry snow, the salty snow interface, or is it actually reaching the bottom? If it's not reaching the bottom, what is the uncertainty here? So that's the question we would like to ask. We are still looking at it. We have the waveforms. I haven't looked at it in detail, but it will be very interesting for us as to see if this is the uncertainty what you're looking at, or if Ku and Ka goes right through into the dry snow, into the salty snow, into the freeboard water volume there. So that will be something like which will be interesting to look at. If this is the hypothesis, which means that we won't be able to get the snow depth, but if it is not, that will be very good for us to understand. Overall, we were out on the ice only for like 22 days out of like 8-9 months. We had like limited course, good snow pits. We had also like terrestrial laser scans, 84 of them. Thankfully, we didn't lose an instrument. We lost a lot of money. Because the instruments, it didn't work properly, but we didn't lose anything into the ocean. So we saved the ocean again. That was it. The brief of how our wintering was. It was very interesting. Scientifically, it was also interesting, although we were not able to be on the ice as much. But it was like it was a life-changing experience for me, both professionally and personally. I must say that I have completely changed personally also, because of not just because of wintering, because of like new people in my life. One of the people is actually in the audience. I can't name that person, but that person has like completely transformed me in my life after that. So thank you so much.
Excellent. Thank you very much, Vishnu. That was great. I love the mix of science as well as the sort of personal side of how you handle 8 months in Antarctica. What a cool experience. All right.
It was a warm experience actually. It was not cold.
A warm experience. Yeah.
Yeah.
I'll open it up to questions. If anyone has Any questions? Maybe I'll just begin. What is the sea ice typically like in that bay that you guys were trying to work? Is the idea that it sort of fractures relatively new? Does it typically form a stable sea ice
No,
cover?
no, it doesn't form any stable sea ice cover because the winds are predominantly from the south.
Okay.
Sorry, from the from the south. So we always used to get like a lot of like breakups and breakouts. Uh, so even if the ice formed initially, it would never be stable. So we had to wait for like many weeks for the winds to die down, and then the ice to actually attach to the shore to be ran fast, and then uh, be out on the ice. But the ice thickness would normally be like max 40-50 centimeters. The max we
Okay.
got was like 45 centimeters,
So
and we had like
it typically grows a bit of ice and then it breaks out, and then it grows a bit new ice, and then it breaks out again and
yeah, yeah.
eats throughout winter.
Yeah, and the level of flooding was also very heterogeneous. It was not like we had like 1 centimeter flooding. We had like snow pits up to we had almost ankle up to like ankle level of water, almost like close to like 5-6 centimeters, almost up to like 10 centimeters. It was like that flooded. Close to the shore though. Close to the shore though.
Yeah, interesting. R2.
Yeah. Hello.
Great.
Hey.
Hey, can you hear me?
Yes. It's been a while.
Perfect. Yeah. First of all, too bad that you're in India. I'm in Canada. So hello from here. Uh, yeah, I think thanks for the great presentation. I think it's remarkable that you didn't lose anything,
Yeah.
like scientifically. Um, Couple of questions. You mentioned laser scans.
Mhm.
What are you using those for?
We were actually using to get the surface roughness, the RMS height and the correlation length to be used for like the for the scattered models. We wanted to see how the roughness from different roughness types. Robbie had designed like a roughness rakes of different wavelengths. So we artificially actually raked through the snow, raked
Yeah.
across the snow, and then used the TLS and also KUKA to actually coincidentally look at how the roughness and also the backscatter changed as a function of different wavelengths.
Okay.
The
Cool.
roughness wavelengths.
Yeah. Right. And another one, I think that this KUK band radar is such a unique instrument. Do you know what is it doing next? Where is it heading to?
It's going to Resolute.
Oh,
It's heading to Resolute end of April. It's actually it will be below. Uh, Sorry, uh, it will be towing. I think Christian Haas is actually flying. Oh, I think RPU will also be there. I guess.
well, in the start, I'll only be in Inuvik. I won't be in Resolute.
Okay, yeah. So it will be in Resolute doing
Okay,
fun checks. Yeah, look
cool.
mostly looking at like on first year ice and maybe looking at slush FX
Mhm.
also probably.
Yeah, cool. Okay, that's all I wanted to know. Thanks, Vishnu.
Excellent.
Thank
Thanks,
you.
R2. Inga.
Yeah, thank you, Vishnu. That was great. Really good to see the challenges of fieldwork as well. That's something that we're often not very honest about in our talks. So I think that was really great to see everything that you went through. It was really impressive, as Artie said, that you got all the equipment back, even if it wasn't functioning. So our group deploys a sea ice monitoring station every year in McMurdo Sound, and it's nowhere near as challenging as what you were doing at Rothera. We've got an upcoming project proposal that we're writing where we're thinking about making more robust sea ice monitoring stations, and I'll be talking to Petra about this as well, and making them so that they could withstand those kind of conditions that you were in. Do you have any suggestions of what might be useful?
When you say monitoring stations, what do you want to monitor?
The sea ice. So it's like the sims that you put out for Petra with the pelican cases, everything.
Yeah.
But we're thinking something that would be more robust, so more waterproof and able to float, I guess, in those kind of conditions.
It was very surprising for us to also see that the IMB got flooded because it was watertight. One takeaway lesson for us was I think it's, I mean, if the conditions are not so bad, I would, if it's bad, I would wait for the winds to die down and then deploy IMV. What we did was, when we had the ice formation, after it was like stable for like a week or so, we immediately put the instruments out. But the Rodra is like a relentless. It's just absolutely, it's relentless when it comes to winds. So, it was difficult for us. So I would say, look at winds and see if it works. If it's stable, then please go ahead and deploy. That's it.
Great. Yeah, I see R2's just mentioned watertight means that the water can't escape once it gets in. Yeah, so we really want completely waterproof so that no more water gets in to start with, I guess. But you're saying it was designed that it shouldn't have allowed water in, but somehow water got in?
Yeah, and I would, and one another recommendation from our side is, which we did during Mosaic, was we always had like CCTV cameras looking at the instrument what it was monitoring. So it's always very useful to have like a webcam looking at whatever you are deploying. So we use that like a lot on Mosaic, which actually helped us also to see like how the snow and the ice evolved. So that was also great. So I would recommend that.
And your data was sent back by Iridium or something, so that you got that week of data back. You didn't need to get the instrument back to get the data, or?
Yeah, or if you are like deploying it closer to the land, you can actually put the webcam on in the land and then look at it like
Oh, I see. Yep.
Yeah, that's also another way to do it.
Perfect. Thank you.
Yeah.
Great. Any other questions? Nothing. Well, if there's nothing, before we shift over to Petra, I wanted to do two things. I want to thank Vishnu again. Vishnu, that was a great talk. Again, all of these are recorded and posted on the IGS YouTube page. So if you can think of anyone who may have been interested in this talk and maybe missed it today, please direct them to the IGS YouTube page, and the talks are available there. And speaking of that, I'm going to share in the group, Robbie Mallet, who joined Vishnu in Antarctica, gave a presentation just about a year ago in this same seminar series. And he was talking about the difficulties in using satellite altimetry to estimate ice thickness, and specifically how altimeters deal with this brine wicking and sort of the uncertainties that introduces. So it's kind of interesting because we got Robbie just before you guys left for Antarctica, and now we have Vishnu after Antarctica. So the two talks are somewhat related. So I shared the link there in the chat, and I'd encourage everyone to go check it out. Both were great talks. So thanks again, Vishnu. That was excellent. And now for a quick little update on the current conditions around Antarctica, we're going to shift over to Petra. And Petra, I'll get you to turn your camera on, or just go ahead and share your screen.
Sorry, guys, I'm working across 3 platforms here. I'm not in my home office. Let me try. Share the screen.
Looks good, Petra.
Does look, and you can understand me clear? Can you understand me?
Yeah, it looks good.
Okay, sorry. Thanks. Yes, so thanks for Vishnu for giving us this really interesting and a bit teary presentation, especially seeing that some of the instruments we put a lot of effort in, and I played a minor role. Those guys with all the design team were really busy planning for that, and it was such a unique opportunity. And then to run into such critically low sea ice was really a bit of setback. But as we have seen, they managed to get really good work going. So I'm at short notice in Melbourne, so I'm greeting you from the Mornington people land and acknowledge them as the owners of the lands past, present, and for the future. And I just want to take the opportunity because we knew that Vishnu had quite a longish presentation to remind us of the larger scale setting. And so recently we have heard about all these emerging tipping points in the Earth system. We had Armstrong McKay and other papers that really focused on those. And so I took the liberty, you can't, oh yeah, it's just a lot of lag to my mouse. Anyhow, I try to avoid using it then. I took the liberty to add some tipping points in here. And for example, the Antarctic sea ice summer collapse, also the increased cryosphere erosion that we have observed across the Southern Ocean, and remarkably also the loss of glacial ice up in the third pole. So there are additions that I annotated to that figure because we have had updated information. In Australia and with some New Zealand colleagues, we recently reviewed tipping points that would have an impact for Australia, and I will talk to that. But I just encourage everyone here to consider what is the change of those cryospheric and Earth system components meaning, and how are they reflecting, and how would they hit on to qualify as a climate tipping point by definition. So as Dave promised, I just want to give a couple of very brief slides showing you the growth curve, the seasonal evolution of the Antarctic sea ice over the satellite record. So in gray on this figure, you see from every January to December the annual evolution since 1979, passive microwave data, obviously. The black curve gives you the long-term mean over those, whatever, 40-something years, 50 years. In the light green, you see, sorry, my mouse is very laggy, you see the maximum occupied in 2014 during the winter. And obviously, the dark green shows you the 2023 records. And both in summer, February 2023, we hit an extreme minimum, and also the summer the winter measurements in 2023 were an all-time minimum. The evolution up to 2 days ago for this year are shown in this bold blue line, 24. 2-3 weeks ago, we narrowly missed another record sea ice minimum for good luck. I guess the press and the general public might be disappointed, but I guess every time we don't break a record is a win for the Earth system and for us researching it. So yeah, be primed of what's happening, especially as we move into those early winter months and then towards the 24 maximum to see how the system evolves. Just for those who are really keen, the anomalies of the same data, basically just the anomaly shows that 24 is tracking a little bit higher up in the usual area, but still very, very low compared to the overall record of nearly 50 years. Recently, you might have seen, sorry, the acknowledgement cut off down here. It should read, Will Hobbs and colleagues published a paper in Journal of Climate 2024, and they were very much concerned about the Antarctic summer sea ice minima, and they studied the 2016 minimum, the 2022 minimum, and then brought it all the way up to the recent record. And so basically they identified on the behavior of the sea ice extent area anomaly that there was a new regime basically that the sea ice was occupying. As you will very well remember from the late early 2000s, so 2008, 7, 8, we saw the first change happening. Then the ramp up in the years 2012, 13, and 14. And then this dip in 2016, a slight recovery. And now the last 3 years, we have these really strong negative anomalies. And so basically, they conducted quite a lot of analysis into atmospheric and oceanic drivers, found that obviously the atmospheric systems are responsible for priming the system, but then really impacting a lot of change in the ocean circulation. They used coupled ocean sea ice model forced with observed atmosphere, and they found that the sea ice minima really are responsible also to the changes in the ocean forcing. So based on that, they carefully phrased that the Antarctic sea ice state has entered into a previously undescribed state of regime. Doddridge, Purridge and Doddridge, I don't have a figure of them here, did a more cursory analysis, but they also very much proposed that the Antarctic sea ice slipped into this new state. I just hit briefly the Arctic-Antarctic comparison over the same record since '79, and that was originally published by Turner et al., but recently updated by Crozer in this Bureau of Meteorology report on tipping points that I just mentioned. And as you can see, and what we have to expect in a global, in a system of so much global warming as we have seen the last few years, obviously the cryospheric components will have to behave the same way. We can do away with this period of the Antarctic paradox where we saw the sea ice seemingly expanding around the Antarctic, and now both systems are really on this strong downward trend. I skip over those figures because we're running out of time, and I just wanted to encourage and invite the community to consider how we can make use and best use of the information that we collect, and to share it with other folks that are probably not spending as much time looking at the data and analyzing the data as we are. And so from our area, we recently, and probably motivated by work with the WMO, World Meteorological Organization, started releasing monthly sea ice report cards. And they are on the internet accessible. They are emailed out, the updates within a few days after the month's ending to a user community. And so we basically are guided to provide a general commentary on the Antarctic sea ice. We refer to relevant regional but also global events. And then we provide relevant updates, how those changes in the system, especially around the Antarctic, impacting the users. And we try to have the same figure, the monthly updated figure, accompanying the text. So this is always at the moment sea ice concentration distribution with the long-term anomaly shown for that particular month. And then we have in the orange and purple on the outside, the sea surface temperature anomaly, which we found the most useful for the people that we talk to use. I very much like to have overlaid also the changes in the atmospheric circulation, but the figure just got too clustered. And then we also provide a summary of the 23, the annual summary. So 2023 was our first full year. We provided those cards, and it's a similar story where we go through commentary, relevant events, and an update for stakeholders. So if anyone is interested to receive those or have input those cards or do something similar for the North, we would be really happy to hear from you guys. And similar, very happy to catch up with Vishnu to hear an update on our poor IMB, but also to talk to Inga and others about how to build robust observatories. And I think that the key is really now robust, because the system has changed so much, and a lot of our previous observing methods are now vulnerable to the elements, which we didn't have to worry about as little as 10 years ago. So I look at the clock and I'll probably finish up here. Thank you.
Great. Thanks, Petra. Thanks for that update and that summary on the Antarctic report card. That looks great. I'll have to check that out. Any questions or any other comments on Antarctic sea ice? If not, I will thank everyone for joining this week. Rob has a comment here in the chat. Annual analyses of Antarctic sea ice are available in the NOAA BAM's annual State of Climate reports. There we go. Excellent. Thanks for sharing that, Rob. Okay, so I think that'll do for this week. Next week, we are back with one of these time-shifted seminars. And again, so the next one will begin at 0100 GMT on Thursday, March 28th. So for those of us in North America, that is still Wednesday, March 27th, our evening. Unfortunately, it's the middle of the night for Europe, so it's tricky. But again, this is in an effort to accommodate the Cryosphere Research Group throughout Asia and kind of give them a better opportunity to join these seminars. So next week we have two talks. One as an introduction to Arctic research taking place in Taiwan and its challenges, and a second talk on remote sensing of the Greenland ice sheet. The next seminar in this regular time is scheduled for April 10th. We have Melinda Webster, who's going to be giving a presentation on geoengineering and snow. And we may be adding a second talk to that. I need to double check the schedule, but we'll sort that out. And as per usual, we'll advertise these on CryoList, and they'll be up on the IGS website. So thanks to everyone for joining this week. Thanks to our two speakers, Vishnu and Petra, and I hope everyone takes care. We'll see you around.
Thanks, Gary.